Good evening, everyone. This is Tony Miracker. I'm the section chair of the Toronto section. Welcome to our March meeting on Atsc 3.0 in 2021. We have a great list of presenters here for this evening, so fasten your seatbelts as this is going to be a great. Just want to point out a couple of things here before we get going. We do have our TTC in the works that will be this year virtually, June the 15th to the 17th. So do mark this in your calendar. Again, the theme will be media fast forward, and the list of topics that we're looking at presenting over the course of the 3 days, and there will be half days, not full days. The changing digital landscape. We've got some UHD, HDR topics, IP, cybersecurity, the cloud, AI and machine learning, and automated workflows and evolution of television and cinema workflows as well. So again, it's going to be a packed 3 days, but it'll be virtual. We will be sending out a call for papers and a call for sponsors for those list of topics. So there will be an email blast going out later out this week. There's a couple of URLs there that you can go to get some information, but that'll all be encompassed in the email blast that we do send out. There will always be updated information at our SMPTE Toronto website. So if I go into tonight's evening, it's arranged by Riza Sufo and Peter Armstrong, and they have co-organized this meeting, and they will help the process of this meeting with and various other tasks. We've got on our list here tonight we've got Urs Schuko from Humber College. We have Madeline Noland from Atsc. We got Mark Corll from Trivine. We've got Dr. Wu from the Communications Research Center in Ottawa, and we have Anne Shayley at Pearl TV in the United States. If I can get Riza to spark up and introduce our first presenter, Urs Schuko.
Thanks, Tony. Yeah, if you want to flip to the next one. First speaker for the evening is Urs Schuko. Urs is the professor and program coordinator for the film and multi-platform storytelling at storytelling program at Humber College, and is a project lead for the Humber Broadband Convergence Lab development. A graduate of McMaster and Ryerson Universities and a Fulbright specialist, Urs' work in television and film sound has garnered him an Emmy Award, 2 Emmy nominations, 2 Genie Awards, numerous international recognition. Urs got his start in audio engineering at Maxter's Workshop in Toronto, working in music, remote concert recording, and post-production. This was followed by nearly a decade of senior mixing and Alliance Atlantis Communications at Casablanca Sound and Pictures. In 2005, he accepted an offer as a lead re-recording mixer with Todd AO Studios in Los Angeles and spent 6 years working internationally. Urs has mixed 7 films for director David Cronenberg and has collaborated with a broad range of directors and producers, including Robert Eggers, Barry Sonnenfeld, Jude Apatow, and Guillermo del Toro. Urs' passions for applied research and development has led to developing functionality in SDK design and architecture or incorporating audio processing. He currently leads the research team as a principal developer in formulating a novel audio watermark technology. And I know it worse from, I'm not going to say how many years ago, but many decades ago, or when we went to school together for audio engineering. So it's odd that an audio engineer is talking about transmitters and another audio engineer is presenting papers, running a presentation for transmitters. So anyway, take it away, Horst.
Thanks very much, Riza, and welcome everyone. It's a small world, and it's nice to come full circle with Tony, Peter, and Riza this evening. I wanted to thank SMPTE Toronto for their tremendous support in putting this evening's presentation together, and wanted to take an opportunity, just a few moments here as a prelude to the main part of the evening, and deliver a brief overview of our ongoing lab development at Humber College in Toronto. I want to extend first off my sincere thank you to all our lead presenters tonight, Madeline Noland, Anne Shelley, Mark Corral, and Yin Wu, for joining us from both Canada and the US this evening. They are all true ambassadors of this new standard, and I'm grateful for their unwavering support for our lab effort here in Toronto. I've had the pleasure of working with each of them for about the last year or so, since we held an ATSC3 seminar at Humber College a year ago last January, just on the cusp of the pandemic. That event served as the impetus for us to set a lab development in motion. So with that, I'm going to leave tonight's speakers, to unpack the finer details of 3.0 and then just provide you a brief high-level overview of what we're aiming for at Humber. So we're excited to be able to start at, hopefully soon, start to put together our first testbed for ATSC3 in Canada, a living lab and an interop site where we can service a host of industries that are interested in exploring and benefiting from the digital transformation of the broadcast system that you'll hear about this evening. That transformation can take place in the form of B2B and B2C models with content that can be delivered on top of the conventional television broadcast. It's essentially a form of slicing up the 6 megahertz station bandwidth into multiple IP streams. We're aiming to stand up the lab and be operational in the last part of this year, barring any delays with the pandemic. So with content being delivered through IP or internet protocol with this new standard, it opens up a lot of possibilities with integration with the broader internet, and effectively brings the broadcast silo down and into the world of the internet proper, if you will. And that leads to the creation of and deployment of both television and non-television applications, along with the global standard, other global standards, including 5G and whatever comes after 5G. So with that, we're looking forward to working with broadcasters and industry stakeholders and exploring ways to develop delivery models that will make more efficient use of both underutilized and perhaps undervalued OTA spectrum and its existing infrastructure across Canada. We're aiming to procure developmental licensing for ATSC3 and 5G spectrum together to offer an in-lab experience at Humber College, as well as an external infrastructure that will give us a multiple antenna, multiple radio system that lights up spectrum in the North Campus area of Humber College. We are in a position where we'll plan to offer 2 ecosystems, that being the ATSC3 broadcast ecosystem and a 5G core network. This is something that's unique to this lab that will help us open the door to developing a heterogeneous data delivery network architecture alongside of an emerging 5G service footprint. We're also planning to work with a portfolio of both Canadian and multinational partners and industry stakeholders. So our central mandate with the lab will be fostering partnerships between Humber College and the private sector, and that's going to lead to development and innovation in the Toronto area, in the Southwestern Ontario area, into the province level, and then into finally the national level. That strategy in supporting growth of applied research capacity leads to greater business collaborations, not only with the college, but between potential partners that come together. So the lab starts to serve as a bit of an incubator or an accelerator beyond just being a test bed and interop site. That in turn is going to facilitate commercialization, which leads to a technology transfer and movement into the marketplace with the hopeful goal of helping to facilitate adoption or formal adoption of 3.0 in Canada. So with Atsc 3 running on an IP backbone, which again you'll hear about much more later this evening, it offers improvements in broadcast mobility and convergence with 5G networks by sharing a common base clock. So the two systems really don't compete, but rather OTA broadcast and mobile unicast delivery through 5G can complement each other in ways that you're going to learn more about. Currently, the OTA and the mobile stacks or the mobile systems operate in a closed stack. So what we're hoping to do with industry is to find a way to open those stacks and consider scenarios such as offloading mobile traffic onto television spectrum, creating use cases with broader internet integration, 5G backhaul and ways to extend data service footprints, and also engage in other areas where the value proposition of a one-to-many broadcast system with the potential for a return channel can come to the forefront. So our lab's going to be situated at Humber College North Campus in the Barrett Center for Technology Innovation. This is a new 93,000 square foot site on the main campus at Humber North. And it offers a lot of potential with current industry and future industry partners in areas of automation, robotic systems, integration services, user experience testing, applied research, and work integrated learning. So we're very excited to have found that, to have found a home for the lab in this particular location. We have an experienced multidisciplinary team that we started to put together. And these particular faculty members come from a range and a host of industry backgrounds, from consumer electronics to mobile and satellite communications to defense and aerospace, geomatics, aerial and ground autonomous systems, biometric systems, interactive media production. And you might wonder what all those have to do with Atsc 3, but you're going to learn about that a little bit later this evening. So I'm providing that information in a general form as sort of a teaser for the rest of the speakers. We're going to be pushing, hopefully, the boundaries of IP data delivery, RF engineering, and interactivity and broadcast, journalism, communications, big data, all that to support innovation in Canada. And what's important for us is that students will be at the center of that experience, and it's going to provide them an opportunity to open up their minds, working with faculty, working directly with industry partners, and engaging in a forward-thinking manner with a forward-thinking standard. There are a number of themes of research that we'll be centering on, including television interactivity, and that's where we'll be working to combine real-time and non-real-time content together, essentially merging the OTA and the OTT experience. That will also include use cases involving addressable advertising and content substitution. With data delivery, we're going to be also focusing beyond the hybrid architecture into geo-targeting and hyperlocalization use cases. And also slicing the data delivery network into a broadcast and unicast pipe. And that efficiency will hopefully come to the forefront and shine as we move into the age of the connected cars and other mission critical applications. In the areas of GPS augmentation, we're hoping to work with the strength of the standard and its offering of precision timing to start to look at signal penetration with 3.0 signal into barriers such as underground parking, canopies, tunnels, where we can augment when satellite coverage is not available. And a big part of our research will be conducted in a joint manner with Dr. Yin Wu and the research team from the CRC in Ottawa. And that's going to involve a couple of key areas, which you'll hear more about in Yion's presentation tonight. That involves broadcast inter-tower communication within Atsc 3, and IDL in-band distribution link, development of a broadcast single frequency network, as well as the eventual creation of a broadcast core network and convergence with a 5G core. We're also very excited to be able to extend our reach into the US and develop creative and technical partnerships with Pearl TV, their Phoenix model market, and the Detroit test beds as well as Michigan State University's Next Gen Innovation Lab. They are connected with WKAR, the PBS station in East Lansing. A keynote to express here to industry stakeholders and others interested in this type of setup is that all the intellectual property cultivated, created, and formed at the Humber Lab stays and remains with the industry partners. And that's something that's very key for a lot of industry partners that have been expressing interest and will hopefully continue to express interest. So with that, I leave you with a very brief introduction this evening, and I'm hoping that you'll enjoy the rest of the presentations. I'm sure you will. If there's an opportunity to connect with anyone afterwards in the Q&A, I'm happy to facilitate further information at this point. So thanks very much, everyone.
Yeah, thanks, Horst. Riza, I'm just jumping in here for a sec because I think I skipped over a slide just to tell everybody that there will be questions at the very end, and also there is a question box and a chat box that if you do have a question, then please drop a note in there, and Peter will pick it up at the appropriate time, and we will have questions at the end. So I will hand it back over to you, Riza.
Great, thanks. Thanks, Horst. Thanks for setting the table for the rest of the evening. Really appreciate that. That's a great overview.
You're very welcome.
Next up is Madeline Noland. And if you can flip slides for me, thank you. Madeline is the president of the Advanced Television Systems Committee Incorporated, widely respected for her consensus building leadership style. She chaired the ATSC technology group that oversees the ATSC 3.0 next generation broadcast standard before being named ATSC president in May 2019. Previously, she chaired various ATSC 3.0 related specialist groups, ad hoc groups, and implementation teams since 2012. A 15-year industry veteran, Noland held key technology management and standard roles at Backchannel Media Incorporated, Teleview Corp, and LG Electronics. She received TV News Check's 2019 Futurist Woman in Technology Award and was named one of 2018's most powerful women in consumer technology by Dealership Scope magazine in 2016, she received the ATSC's highest technical honor, the Bernard J. Lechner Outstanding Contributor Award. She graduated cum laude from University of Massachusetts. Sorry for butchering your bio, Madeline, but thank you for joining us, and please welcome Madeline.
Great, thank you so much, Riza. And just to confirm, can people see my screen?
Yep, there you go. Yep, that's great.
Okay, great. So first of all, I want to say thank you. I also want to say thank you to Orest, who has been incredibly enthusiastic and has just poured so much energy into this effort. And that started the fall of 2019 when he contacted me and said, hey, I was at WKAR and I thought it was pretty neat and we're interested in looking into this. And I thought, well, that's fantastic. We should definitely support that as much as we can. And then we dreamed up this idea that the ATSC technology group meetings and board meeting would take place in Toronto in January. Well, that went over kind of, it was kind of funny when I told all my colleagues that we're definitely having all of our meetings in Toronto in January. But I'm very pleased to say that not only was Humber College a tremendous host, but the weather cooperated too. So we're very pleased to have been there, and as Orest points out, it was on the cusp of the pandemic, and we feel as though that trip to Toronto in January of 2020 was one of the best trips we made. So thank you to Orest and thank you to Humber for all the support for what we were up to. As Orest mentioned, I think what I'll do here is give a quick update into what the standard is, what it does, and what ATSC is up to continue the support of the standard. And then I think I'm going to turn it over to into the capable hands of Mark Corral and Dr. Wu and Ann Shelley, who are going to sort of dive into different aspects of either the technology or the deployment. So to start with, I think we'll just give you a quick introduction to next generation TV. And ATSC is a standards development organization. We have about 140 members or so, which hail from across the globe, including Europe, Asia, Canada, other areas of North America, etc. One of the most exciting things was that there were nearly 400 active engineers who were participating in the ATSC 3.0 development process from all over the world. And I know from my own experience representing companies within the ATSC 3 development process that there were many, many team members behind each person that was participating in the process. So we're so excited because what we came out with was truly the best of the best. And the ATSC 3.0 data delivery system is absolutely state of the art. So let's put ATSC 1.0 in perspective. As many of you probably know, ATSC 3 is non-backward compatible with ATSC 1. So why would we do this? Well, let's think a little bit about where we were when ATSC 1.0 came out. Well, we had Windows 3.1, we had dial-up modems, which did 19.2 kilobits per second, which for its day was pretty good. We had analog phones, which were pretty big and heavy, and we had tape decks, and we had ATSC 1.0. So you can imagine that it might be time to take the step forward in technology, and perhaps maybe high time. But ATSC 1.0 has been a wonderful standard. It continues to be a wonderful standard. But we needed to think about what is happening in our world today and how can we modernize the television broadcast airwaves. So thinking about the goals of ATSC 3.0, as I mentioned, it's not a backward compatible system, and it's also a voluntary transition. So when you have a non-backward compatible system in a voluntary transition, it had better be good. We definitely wanted to add value to the broadcasting service platform. We definitely wanted to address changing consumer behavior. But one of the most important things that the designers wanted was, hey, you know what? It's about television, but not just television anymore. It's about a lot more. So we're going to be able to talk about much of that, and many of the other presenters are going to get into it as well. So here's a summary of ATSC 3. This is truly the elevator pitch. What is ATSC 3.0? Well, it's a new physical layer, different from the ATSC 1.0 physical layer. It is flexible and configurable and is currently the world's most efficient one-to-many broadcast system out there. It comes closer to the theoretical limit of how much data you can push through the airwaves compared to a signal strength of all. Also, the transport is IP-based. Again, another first in the world. This is the first digital transmission broadcast system which is based on IP. And we do have two transport protocols, the MMTP and the root dash. And of course, one of the killer apps on television is naturally television. So one would want better video, better audio, interactive apps, more accessibility, and advanced emergency messaging, which allows us to update and recall messages, as well as send information in rich media forms such as web pages and videos and audio tracks, and also allows us to wake up receivers and allows us to do some geo-targeting with our emergency messaging. We also have data casting, which kind of comes hand in hand with a better physical layer and an IP-based transport. So we figure that we're delivering bits, and whether those bits are streaming television linear services or whether those bits are software updates, as far as the ATSC 3 system is concerned, it's all good. So we have the ability to deliver data to basically any kind of device, and that could be cars, smart agriculture, digital signage, smart cities, and more. And the other piece is that it's convergence ready, which is another very important part of ATSC 3.0. It's designed to easily interoperate with other IP data delivery networks. So you imagine a heterogeneous network system where you have 5G, you have LTE, you have Wi-Fi, Bluetooth, the internet, and ATSC 3.0. So it's designed to converge with those systems to enable a variety of use cases, many of which Orest described that the lab is going to be looking into. So thinking about data casting as a service, it's really a large digital data delivery pipe. And single frequency networks, which are also part of the standard, definitely allow even more data to be pushed through by making the signal stronger. And terrestrial broadcast could potentially compete with other data delivery networks and/or complement those using price and service level for the one-to-many use cases. So the data casting is quite a powerful feature of the new system. There's a little bit here about deployment, and I think Anne Shelley is going to share more. But up to now, the broadcasters have announced in the US that 62 market areas will be launching ATSC 3.0. And because 40 of those are the top 40 markets in terms of population, when we reach those 62, we will be reaching roughly 75% of US households. And the map here shows our progress to date. I shouldn't say our progress, I should really say the broadcasters' progress. Where the orange markets are the ones that are on the air with broadcasts today. The blue ones are the ones that have filed with the FCC for their license to do so. And the dark blue ones are the ones that have announced but haven't yet filed for the FCC license. And as you can see from this screenshot, that you can keep up to date at the ATSC website under Spotlight ATSC 3.0 deployments. And we update it all the time because I love to check this stuff, and so I check it all the time, and whenever something new happens, we make an update. Also interesting to think about from the TV service point of view, what's going on with the device market. This is research that was put forth by the Consumer Technology Association about the current and expected sales of television sets that are equipped with next-gen TV capability. And as you can see from the slide, we've shipped about 300,000 in year one, and that's looking to ramp up very nicely between now and 2024, with the cumulative effect of being roughly 24 million television sets in the US with next-gen TV capabilities by 2024. There is also some research suggesting that these numbers might grow even faster than this. That would be nice. In addition to television sets, there are other devices coming out on the market for consumers. There are two set-top boxes, or gateway boxes, if you will, that are available today, the Zapper Box and the HD Home Run Connect. And then there are some white label boxes that are being developed as well, such as the Zinwell, which has been used for distance education in particular, as well as other use cases. And there are new chipsets coming on the market, and there are a lot of exploration of very low-cost converter boxes as well. So we'll see how the market develops. There's also international interest in ATSC 3, and here we are in Toronto. So South Korea launched commercial services in 2017, and they are currently reaching about 75% of their households. In fact, they're going to turn ATSC 1.0 off in 2027, according to their plans. So as you know, Canada is exploring ATSC 3.0. Humber College in Toronto is developing plans for the Convergence Lab. CRC in Canada was actively involved in the development of ATSC 3.0 and continues to innovate on inter-tower communications, which Jan's going to speak to. And NEBA is also working on forming a new work group on ATSC 3 usage in North America. In Brazil, the SBTVD Forum is evaluating ATSC 3 and other proposals for their TV 3.0 transition. And ATSC has a Brazil implementation team, which is organizing the support for the ATSC 3 proposal in response to their call for proposals. In India, TSDSI is studying ATSC 3 and other technologies for broadcast traffic offload and direct-to-mobile media services. And the broadcast traffic offload scenario harkens back to what Orest was saying about a converged broadcast unicast ecosystem. And there's an ATSC India implementation team which is supporting that effort. And then a number of other countries have also sort of reached out to say, hey, what's up with this? So South Africa, Dominican Republic, Mexico, Australia, and others have reached out. And we have a planning team on global recognition of ATSC 3, which is coordinating those engagements. And we also have ATSC 3 related submissions going to the ITUR documentation, which is also being coordinated within Planning Team 6. But I think one of the most important things that I want to impart to everybody today is that ATSC 3 is a platform. So unlike previous DTT standards, this platform can evolve. So you can think about how web browsers or even your Netflix app or whatever can be updated pretty frequently. I don't know how many times my computer updates itself, my phone decides to update itself every 6 months. We need to be able to do that also in order to be able to keep up with the rapidly changing landscape. So ATSC 3 has to continually develop so that the broadcasters in the broadcasting industry can continue to serve the market demands. ATSC maintains and develops this platform, And happily, many ATSC members are based in Canada. And the other good part about ATSC is that all of the ATSC members pretty much are users of the platform. So hopefully they're busy making the right decisions about where to take it. There's lots of room for innovation in today's standard. So there's the web-based interactivity, which is limited only by people's imagination. There's the broad range of video, audio, and accessibility features that can be rolled out. There's automotive, IoT, and all that which is ready to go and good in the standard as it is today. So if you think about what we're working with right now with the ATSC3 standard and what's out there in the world, both in South Korea as well as the early deployments in the US, we're really just scratching the surface of what the standard's capabilities are. But even beyond that, we have to think about what's next. ATSC has to stay on the vanguard of what's coming in the future. So we can't wait for the market to demand something. We kind of have to anticipate it. And one of the things that we did was we made it a little bit easier for us. So we built in a lot of opportunities to evolve the standard in a backward compatible way. So we have a modular document architecture. We have the extendable foundation technologies like the XML signaling tables. The Bootstrap is critically important in terms of what receivers, quote unquote, get hard coded to know or not. And we have the Bootstrap also enables receivers to skip stuff that they don't understand. In other words, the evolutionary things. And we have physical layer pipes, which allow us to kind of deliver older services, newer services all at the same time in the same RF band. So we get to continually upgrade ATSC 3.0 without orphaning the legacy devices. And that's super important because ideally we can grow this standard without going through another non-backward compatible change. Just one example of the tech under the scenes, and this sort of is the tip of the iceberg because there are many, many examples in the standard that allow us to evolve the standard gracefully. Here's a diagram of the Bootstrap. So the Bootstrap is the thing on the bottom there, and it tells you the time to the next frame that's going to be very similar. So for a receiver that understands today's data and might not understand whatever comes next, who knows what Humber's going to come up with, or it's just going to come up with something crazy, and the receivers aren't going to understand a darn thing about it. And what it allows you to do is it allows you to interleave that type of information with the information that the receivers out there today understand, and it allows those receivers to pick up the frames that they do understand and skip the ones they don't. So this is a neat innovation within ATSC 3.0, and as I mentioned, it's just one example. The next thing I want to talk about a little bit is what we call a core network. So this is another area of development within ATSC that we think is going to be critically important for the future of the standard. So if you think about a core network, you think about, well, we've got ATSC 3, and that means we have this nice, big, nationwide wireless IP data delivery network, right? Well, sort of. Actually, we have a lot of wireless data delivery network nodes. And one node doesn't make a network. So thinking about the core network functions, the cellular network is a really good example of a core network. And I know that the Humber Lab is intending to build a 5G core network in order to work with it. So the core network is going to perform a lot of things. It essentially ties the towers together so that you have a network of towers instead of a single tower. It authenticates the receivers, it routes the data to the towers, manages the data sessions. It's kind of the gateway to the external networks, like in this case, the internet, if you use your cell phone to call up internet pages. It's the gateway to other cellular networks. So if I'm a T-Mobile subscriber and I'm in a Verizon world, it kind of handles all that. It manages switching between 3GPP and non-3GPP networks, like when I start my call in my house and I'm on Wi-Fi, and I leave the house and drive away, and it seamlessly switches over to the cell phone signal. Tracks the usage, and it does all kinds of other things. So the core network is pretty fundamental to the cellular network. So 3GPP standardizes both the radio access, in other words, the physical layer, as well as the core network. And ATSC is starting to undertake work on a core network. So why do we need a core network for broadcast? Well, like I said, are we having a nationwide wireless IP data delivery network yet? Well, actually, we have 210 market areas in the US, and we could say that we don't have one. We actually have a lot of individual data pipes. So the core network can coordinate the data transmissions among multiple towers. And the broadcasters can work together to form one or more regional or national broadcast networks, essentially creating almost like a broadcast network operator. And so when you come down to it, ATSC3 plus a core network enables the new nationwide wireless IP data delivery network that we think we have. So what can we do if we have this core network as broadcasters? Well, we can offer data delivery services to national and regional customers in a very efficient way. We can offer broadcast traffic offload services to two-way network operators. We can offer, for example, backhaul services to other towers and more. So the core network functions enable all of these use cases. So even if we have a lot of nodes, even if all these markets light up that we're expecting, we get more coverage and more depth and expand each market, but we still need a network. What we really want is something that looks like this, that covers all the significant areas and major arterials and connects these pipes together so that we can efficiently serve data on a nationwide or regional basis. So a quick scenario, traffic offload. TSTSI, which is India's telecom SDO, is exploring traffic offload for India. And it's kind of interesting. They have 1.2 billion cell phones in that country, and people watch linear television content on their phones all the time. In fact, a lot of people in India don't have televisions. They only watch TV on their phone. So cell phone ownership and data usage is always going up. So the concept is that you could have a smart network core monitoring the number of devices receiving the same data at the same time on an LT 5G network. Imagine the cricket match. In fact, the cricket, the India cricket playoffs, I think garner somewhere between 25 and 30 million concurrent viewers. So when the number of devices exceeds some threshold, data delivery can be moved off of LTE 5G onto a digital terrestrial network. There's no simulcast. Bandwidth savings is the goal. And the idea is to free up space on the LTE 5G network for unicast services or two-way services and use the broadcast network for the one-to-many use case. So Indian operators are experimenting with 3GPP broadcast mode, including eMBMS, while also exploring ATSC 3.0. And that was kind of a lot of information, but we have a lot of resources available, and I will definitely make these slides available. I can pass them to Riza, who can hopefully distribute them. We have the deployment map, which I showed earlier. We have the B2C messaging for NextGen TV, which is watchnextgentv.com, which is a consumer-facing site, which Anne will probably talk about. There are classes, webinars, and handbooks, and technical documents, and A300 offers an overview of the system and a description of all its components. So I encourage you to avail yourself of these resources for more information. And I'll conclude, DTT broadcasters are operating in a global ecosystem of converging networks. Data session, steering, switching, and sharing across heterogeneous networks can improve spectrum usage efficiency. Use the most appropriate network for each given data session in a dynamic fashion. ATSC3 is the most efficient physical layer for one-to-many data delivery in the world today. It's designed for TV and non-TV, fixed and mobile, one-to-many downlink, and convergence. A core network for broadcasters is going to allow broadcasters to really participate in the global converged network ecosystem. And there are many opportunities as ATSC3 is launched, developed, expanded, and evolved. And Humber College is going to be a big part of that. I know it. So with that, I'll turn it back to Riza, and I guess we're not doing Q&A just yet, but I imagine that's coming soon. Thank you.
Thanks very much, Madeline. Appreciate that. Very robust update and overview of ATSC3, where it is today and where it's going. That's fabulous. Thank you. Next up, Mr. Mark Cole from Treveni Digital. Mark is the SVP of Emergent Technology Development in Treveni Digital, focusing on strategies to addressing the disruptive changes in TV technology caused by the continuing exponential advances in computing and networking. His recent focus has been directed toward media distribution innovation, primarily leveraging the new capabilities offered by ATSC 3.0. Mark is an ATSC board member and contributes extensively to the ATSC efforts as the chair of the S38 Specialist Group on Interactive Environment, the chair of the India Implementation Team, and the vice chair of the TG3-9 Ad Hoc Group on interlayer communications in the ATSC 3.0 ecosystem. Mark is also a contributing author to multiple other standards within ATSC. During his 23-year tenure at Triveni Digital, Mark has led both project development efforts as well as custom projects. Prior to Triveni Digital, Mark had software engineering positions at Texas Instruments and Xerox Corporation. Mark holds a BS in mathematics and computer science from Bucknell University. So take it away, Mark.
Thanks, Riza. Let me make sure I get my screen up here. Okay, hopefully you can see that.
Yep, you're there.
Let's go into presentation mode. All right. Clean off my screen a little bit here. Okay. So I'm going to take us, Madeline and Orest have given us quite a good overview of the standard. I'm going to take a deep dive into the interactive environment. Orest mentioned that one of the goals at Humber was to actually look at interactivity, and interactivity is one of the things that ATSC 3 allows or enables. That's a little different than the other standards, and it's baked in, and it allows us to do more hybrid activity with OTT and OTA. One of the things I wanted to talk about first was just what we've done in the standard and give a brief overview of the standard. Then I'll talk a little bit about how the data is delivered and how the architecture of the, since this is a SMPTE group, how the architecture of the sort of studio setup is done in a general ATSC 3 environment. And then finally give you some examples of what has already taken place and what we've already experimented with and done in proof of concepts. So starting out, let's talk a little bit about what the key goals for the interactivity system in ATSC 3 was. So we wanted to define an environment that allowed broadcasters to enhance the consumer's user experience, primarily around personalizing content, establishing an individual viewer relationship with that consumer so that the consumer actually saw things that were intended for them individually, much as you get with the internet now, where it'll find advertising and find content for you and provide things like that. We can do that now. And it improves the service offerings through feedback, so we can actually respond to people and have people phoning home, in essence, with a feedback channel from the receiver. So the app can actually talk back and communicate through a back channel mechanism if the TV is connected to the internet. And it harmonizes the internet and TV viewing experience. So we can actually pull information from both an OTT and an OTA simultaneously and interchange them, and there's been demonstrations of that at various trade shows and even deployed. And finally, the interactivity system needed to ease the broadcaster and receiver manufacturer development burden. In the past, things have been proprietary. They've been based on technologies that were difficult to program or perhaps specific to the development of the TV. So folks had to build software specific to the broadcast environment so that they could actually run the applications. And that just doesn't play particularly well going forward when all of the developers out there are looking at internet applications. So the standard itself, there's a number of standards. There's about 20 documents roughly in the ATSC 3 standards suite. The ones that really talk about interactivity are A344, which is the actual interactive content document itself, and A338, which is referred to as the companion device standard. And a companion device, I'll go into it a little bit later, but a companion device is essentially a smartphone or some other device that's connected over a Wi-Fi system or some other internet connection to the TV. So the TV would act as a primary receiver and then communicate with what's referred to as a companion device. And this was a notion that's been created and crafted in other standards as well. So other support for interactivity includes the 331 standard on signaling, delivery, synchronization, error protection. That has where all of the tables and what's sent to the broadcast to figure out what's in the broadcast. 332, which is service announcement. That's the ESG or EPG, as you'll know in your table or in other environments. 336, which is content recovery and redistribution scenarios. I won't go into those in detail, but essentially in Atsc 3, we can supply a watermark that allows things that are on the other end of a set-top box or something of that nature to pick up an audio or video watermark and then go out to find the content that they're interested in having locally. And you can actually bring in the interactivity from that control and that signaling information. There's a mechanism for sending events in the broadcast that can be directed toward the application. And then finally, the Atsc 3 security and service protection. Everything that's done over broadcast is secure. We can sign everything. In fact, we're required to sign everything. And we're sending applications, HTML5, CSS, et cetera, over the broadcast. All of it can be found in that URL there. And again, like Madeline said, we'll make these slides. I'll certainly make these slides available for folks that are interested. So some of the key features that are in the interactive content standard, it describes a conceptual application operating environment. So one of the things we don't do in Atsc 3 or in Atsc is define standards for CTA or consumer electronics equipment. So what we built was essentially a call it requirement suite for those devices, and implementers are allowed to do. They can implement most of it, and we do have there is a mechanism that Anne might talk about or others can talk about in terms of how receivers can get their label in terms of supporting all of this stuff. So really, one of the differences in this standard was that we chose to base all of our control and interactivity off of a W3c User Agent, which, if you think about a user agent, think of your browser. All browsers are essentially user agents. That's just sort of a term that we use. We don't have browsers on televisions necessarily, but we have a user agent that will render HTML5, CSS, and JavaScript. And so all of the interactivity done in Atsc 3 is based on standards defined by W3c. It supports seamless secure delivery of the interactive content, as I mentioned. You can either use in the broadcast where we sign, or in broadband, where we'll use basically a standard HTTPS or other techniques to secure the delivery of the data. Each application can run in a separate, unique context. So on the receiver, there's separate cache areas, and I'll talk about that in more detail here shortly. And how the application, we'll call it a broadcaster application. I'll define those shortly as well in the next slide. They communicate with the receiver through a WebSocket API, and so that allows the application to do things like set the video size and push back and things of that nature. It also enables distributed receiver architectures because all of the information is served up via standard HTTP and WebSocket APIs, and so all that information could be on a remote device or it could be local to the television. So here's some key concepts in 344, and I talk about these almost in second nature these days. I've been chairing the committee for I think about 5 years now, so a lot of this stuff is second nature. So the first thing is the broadcaster application, which I mentioned. That's basically just, think of it as just a web page. It's HTML5, including some JavaScript and CSS. Now, there's nothing that says in the standard that there has to be a display, that there has to be some information displayed. In fact, an HTML5 could run that displays nothing and just runs JavaScript and does things that we'll talk about shortly to do things to personalize the viewer's experience, for example, without ever making it self-evident. Some of the other things that are there, the receiver, the W3c User Agent, as I mentioned, it's more or less think of your browser, and it runs the BA. Now, the broadcaster application is based entirely that user agent is defined by a CTA document, CTA 5000, which comes out of what is referred to as CTA Wave. They define that standard, and we simply refer to that. So it's in close collaboration with CTA that we've built this system so that the CE manufacturers and Atsc have been very close in terms of developing this. So we're all sort of on the same page, as it were. And so the programming aspect of that, building of the HTML, is, in fact, you can actually do a lot of that work and run and show in a standard development environment, run it on Chrome, run it on Firefox, on Edge, and it will work very well on an Atsc3 receiver. Now, clearly, you can't just build a web page. That's not going to look, you have to customize it to making it run on top of experience, right? The experience is different. Like you wouldn't program a YouTube video and have a bunch of stuff laying on top of it, because the key is the video. But you can enhance the video. You can do things with JavaScript to make the environment more palatable to the consumer. The receiver is a web server. So the way this whole system works is that broadcasters, in essence, publish web content, such as BA, in secure signed NRT data streams. So the data delivery streams that Madeline talked about can be used or are used to deliver essentially web content to the receiver, and the receiver serves that up as an HTTP stream. So the application itself doesn't really know that it's running on a receiver per se. It just knows that it came up in this user agent, and it knows how to find things to talk to, namely the receiver. And once it's launched by the signaling, which is defined in A331, the receiver, the application launches, and then it discovers where it is, and it starts operating, and perhaps connecting to the receiver, or just simply displaying content as necessary. And as I mentioned before, each broadcaster application operates in a separate, call it a sandbox, called the application context. And then I'll talk a little bit more about this WebSocket control and notification interface. So here's a pictorial example of that sort of architecture that I was talking about. So you see at the lower left-hand corner here, you see the NRT broadcast, or you can have a broadband download from the internet. Either works. The application goes into the application context cache, and then the receiver just serves that up as a web server. So the user agent doesn't know that the content either can come from the internet, or it can come, we can actually serve it up. We can host the broadcaster application on the internet, or we can host it on the application right on the receiver. Either way works, and both work, as a matter of fact. So you could actually have the broadcaster application sent over the air, running in the user agent on the receiver, and then once it's detected that it can actually reach the internet, it could go out and load additional information off the internet if it wanted to. The broadcaster application runs no different as if it was running in a browser or if it was running on a TV, which is one of the beauties of this, is you can develop content intended for television and test it and work it on your Chrome browser, on your laptop, for example. And then the communication here on the right is how the broadcaster application works with the receiver to do various operations. And that's done through the receiver WebSocket server. So this is a model of how the display works. So one difference there is in the user agent is actually the screen itself, the video is running in what we call the receiver media player. So the receiver is getting the content in, it's getting the service in, video and audio, it's running that in an engine that's called the RFP, it's playing, and it could be 100%. And I'll talk a little bit about what's here on the right side stack, but essentially if you look at the left side, you've got the video playing in the background, you've got a transparent background. The body of the application is made transparent, so essentially you can see through it, and so you can see the little question mark there in the corner, which you can consider a bug or something that somebody could press on, and the result is this composited display at the top. One of the operations we have, and it's called out here as an HTML5 document, where we've set up a sort of an opening in an opaque panel. That opening is intended to show the video underneath, And there's a WebSocket API request that actually allows you to do pushbacks and scaling of the video, and you can move the video around, so you can do an L-bar, you can do things like that, and then show on top of that the graphics that are generated through HTML5 requests, the document. You can see those there, that div that's shown, and you get the composite display that appears on the right-hand top of that column. Here's an example, or at least a sort of a pictorial representation of the multiple context application contexts. So the idea would be that if you were switching channels around, the receiver could maintain the documents and the files that have been downloaded over NRT into separate areas. And so what this keeps from happening is that if multiple broadcasters in a DMA or in a marketing area, in a local area, are actually broadcasting different applications, what you don't necessarily want to happen is them all landing on top of each other. So what the cache does, and now they could collaborate and they could actually have the same context cache and actually use that cache if they so desired. But this allows them to separate themselves into separate spaces. And the notion being that if you switch channels, switch services, a new cache can be brought to bear. And if the receiver has enough memory, it manages its cache, and so you could actually switch channels and have the application running again very quickly, because it would already be in cache, it would already be loaded, and they're just switching around. So essentially, each broadcaster application runs out of its own, I'll call it sandbox on another slide, that's as good a notion as any. It's running out of there, and this document, or this diagram gives a view of that. These diagrams are actually, the last three diagrams are actually directly out of the A344 document. So, and it's described in detail there. So if you want more information, you can either wait till the end of the question and answer, or you can go read the document, or both. So some of the WebSocket API features that we have are really a number of things here. This is a very top level list. So we have a number of receiver query APIs so that the broadcaster application can find out what the preference settings are and other information about what the receiver is doing. It can gain access to signaling tables. It can gain access to the ESG. It can do a variety of things like that. It can actually gain access to the advanced emergency information table that comes up from the signaling. They can also receive notifications for all of those if the receiver changes anything, or if somebody's gone in and changed settings. It can be notified of those. It can also be notified of events coming in. There's a variety of things that notifications happen up from the receiver. There's a number of controls that we can do. We can change services. So in other words, if there were .1, .2, .3 subservices within a broadcast, it's possible for the application to switch between them, and that allows for personalization. You can select audio tracks. You can set the volume within certain constraints, and request content to be played back. So if you can implement a VOD system, for example, and you can, as I pointed out before, you can scale and position the video window. And there's cache management mechanisms in the system, and so you can tell which things you want there. You can actually set filter codes, which allows us to send down different content in the broadcast and be able to select between them and have the receiver only cache the things that are of interest to the particular broadcaster application. And finally, there's a number of other mechanisms here. We can manage the RMP, the receiver media playback, so we can actually ask for things to be played back, and there's content replacement mechanisms in the APIs, as well as VRMP management. And I'll talk a little bit more about some of these later in the examples. So a quick overview of the companion device concepts. So the companion device, think of it as a smartphone, a tablet, those types of things. The protocols allow us to communicate with the receiver, so the receiver can discover those applications in there. There's mechanisms to do that. The receiver, the CD applications, the companion device applications allow them to communicate with the receiver. And what we've done is enabled some of the WebSocket APIs that I just went over. We've enabled some of those so that companion devices can also talk, so selecting service, for example. And the receiver can, if it's identified a command device, it can actually launch and notify CD applications on there, and it allows the broadcaster application to talk to the CD application. So I'll show you an example of that here shortly. That's just a nice way. The companion device is a nice way to actually, we found that on receivers, a lot of interactivity is difficult with the remote controls that come with receivers, and it's a lot easier sometimes to handle a smartphone and interact with the television through the smartphone. And the companion device allows such things to happen fairly easily. So this is a studio equipment example. This is very functional level, it's very top level. And in the, you'll look at the top level there is really the video audio chain, captioning chain across the top. So content comes in, you see your encoders, this thing called a packager. Now the packager is exactly the same packager for most vendors that they use to drive OTT video, because as Madeline mentioned, we use dash or dash mechanisms, or that's how the video is encoded into segments. And we use either MMTP or we use route to encapsulate those ISO-BMFF video segments into essentially streams that can be pushed. And so those interfaces up there at the top is essentially that real-time MMT encapsulator, basically wraps all of that stuff up and puts it into a broadcast gateway that then sends it out over to the exciter and the transmitter. So again, these are very fine details that I don't really want to spend too much time on, but really down below that is the signaling generator, the announcement generator. These are almost always all placed into one box, or they can all be virtualized. You can run them in the cloud, you can run them in locally on-premise VMs, you can run them in physical boxes if you like. So most of the systems are moving in that direction and already have. So you'll also see down at the bottom, we have NRT data scheduling along with the AEA aggregation from EAS IPAWS, which are US mechanisms in EAS. And that'll come in and also be populated in the signaling generator along with the wake-up bits. Also down below, you can have the interactive application. So really the intent of this was to show how the interactive application got from the broadcaster through the NRT system, through the broadcast gateway into the transmission, and then able to be received. Now, the interesting thing about ATSC3, as Madeline pointed out, is it's an IP-based system. So broadcast gateways are actually very similar to routers. They take in IP and then frame all that up, put it all together so that it can be pushed over a transmitter. But what the receivers do is they extract from the RF and from the what's called the ALP, or the link layer protocol, they extract all of that information into IP. So essentially, from the start of the system all the way through, once you get out of the PHY layer, you essentially have IP. And so a lot of things on the other side, if they know how to decode and find all the IP multicasts, they can decode it. So the gateways are very similar to just routers. Similarly, then so as the interactive application gets over there, it lands in the cache, and then the signaling generator tells it to start. And that's what, how it generally, in a very top level, works. Here's an example. I'll get into the examples now. So we have the broadcast application. In the case here, if the keys are not present, now there are some examples where the keys are actually present. They're being baked into, some of the keys are being baked into receivers at this point. But if the key is not available for a digital rights management system and the content is encrypted, the broadcaster application gets in the act. So if the receiver media player, the thing at the very bottom there, tries to find some encrypted content and doesn't have the keys for it, it'll basically go to what is called the content description module, which then in turn says, oh, I don't know how to do that. And so what it does is it contacts, up through the system, contacts the broadcaster application. There's actually a notification fired saying, I don't know what this means. I don't know what this content, I don't know what this key means. I don't know how to decode this license. Could you please go out and get me a key for this? And so the broadcast application either goes out to the license server or contacts the consumer and says, I need a key, please give me a key. And then it, if it has the license, it responds and pushes back. And there's a whole recommended practice for how to do this, and that's where this diagram is taken from. And so you can take a look at that if you're interested in more details. So another example that ATSC3 is really pretty good at is the ATSC Advanced Emergency Information. Now, this shouldn't be confused with Advanced Emergency Alerting, or EAS, as it's called in the US, because it's really about getting information about emergency or active emergencies going on in a broadcast area. And it's generally supplied by newsrooms in the US. So one of the first things is the wake-up field, which is carried in the Bootstrap. So receivers in standby mode can find that Bootstrap signal, can decode the see if there's a wake-up bit there, and decide whether or not, depending on what the settings are of the receiver, decide whether or not to wake up and see if there's any information available for it in the Advanced Emergency Information Table, the AET. And that has everything the receiver needs to know, including location. So if the receiver wakes up, sees the wake-up bit, goes and takes a look at the low-level signaling, which is where the AET is at, and says, oh, that's in something, I'm not in that region, it can ignore it and go away. Or it says, oh, wait, that's something I really need to know. It can wake up the receiver, turn it on, or do whatever the user has programmed it to do, and tell the user that there's a problem. The other part of AEA is the interactivity gets involved because we have access, as I mentioned before, the broadcaster application has access to the AET information and all the rich media it may point to. And finally, the watermarking allows us to traverse legacy HDMI systems as well. So we put together, my company put together a thing we call the Aea Manager in collaboration with NAB pilot. And this is just a quick, and so if you'll remember back to the earlier diagram, we had the EAS receiver, which actually outputs a sort of a limited form of the AEA, AEAT. We have the HEVC encoder, all of the OTT packager information that comes into our transport encoder, and we add information about what's going on. So that information goes to the manager server, which then is talking to a client, and that goes out either over internet or the broadcast or both, and then lands in a what would refer to as a BA framework, and then there's an AEA component that runs on top of that. So I'll show an example of what the Aea Manager UI looked like. So what happened was some alert comes in, and the user could basically lay out this display, put up the prompt and things like that. And what happened on the receiver was that there'd be a little, if this was in place, if this application was delivered, there'd be a little bug that would come up on the and lower corner, indicating that there was an emergency in progress. And the user could click on that, and then this display would come up on the receiver. And then the receiver would go to live coverage or could dismiss it, or the user could go to live coverage or dismiss it, and they would get something like this on the display. So it would take over the video and display things, and you could actually go and find evacuation maps, you could figure out shelters, and this was just done as an alert for Santa Barbara when they had the mudslides a few years ago, and would explain how it. So this was just an example that was done, but you could have laid it out in any way. You could use video, you could use all kinds of different media, and this was shown for a particular example for an AEA for an alert. So the next one we did was actually for MSU, and we were basically what we wanted to do is take a STEM program. So they have an interesting program that they've developed, which is just video and audio targeted at middle school kids. And what we wanted to do is basically take that program and expand it and add interactivity, basically gamify it. So what we did was we took that and we added applications to it. So with a set of application files, the application would go over, and then we had companion devices that would figure out that the application was there. And then what we did was we put questions. So essentially the broadcaster application would see events in the stream, and it would ask questions of the student. So as the questions came in, you could see on the phone and the tablet that they would pop up, and students could select the answers. And it was all synchronized with the video stream. So as the host or the presenter was talking about various aspects or had taught some lesson or taught some fact, then the tablet and the phone would pop up with that fact and say, or multiple choice question and say, what was asked? What do you think the answer is? And the idea would be to put up, the host would pose a question, they would run an experiment, and then they would get the results. And the question was asked, what do you think the results are going to be? And what we ended up doing was then tabulating those results from various phones and tablets back onto the main receiver, and then ultimately that would be sent back to the broadcaster, indicating who was interested in playing the game, who was interested in looking at the content, but more importantly, that there had been people looking at the content. And you could characterize how many people had looked at it and how many actually were absorbing the content and how well they were absorbing the content. So this is still an ongoing experiment that we're working with them on this. And here's sort of the display. This one happens to be very topical, unfortunately. But you can see that it would come up, you would submit the answer. Now this could either run on the big screen if there wasn't a companion device, or it could run on a companion device. So one of the other things, and the last thing I'll go over here, is the content insertion concept. So if you look at this, you think of these little red and, blue and green things as segments in an ISO BMFF file. It's viewed by an MPD, which is the media. Can't remember the title right off the top of my head, but basically it describes the playlist of the media, and that's what's sent over to the receiver. You'll see here on the right-hand side. So the encoder packager builds all of this stuff. It sees a splice event, so it wants to put in a break. It tells, oh, here's where the break is, and the encoder basically has to set it up so it's easy for the swap in and out. And what it does is it puts that random access point at the edge of a segment. So you'll have essentially this period where there's a wrap in and a wrap out, so that you can actually do a splice there. And what is put into the MPD is an X-link. So the X-link is a way of telling the broadcaster application it's time, or you have an opportunity here to replace content. That X-link is set over the broadcast along with the content. It's just continuously streaming. The broadcaster applet sees the X-link in the period. It gets that information and then finds, oh, I have another alternate period. Now it will go back to some sort of information, or it does it locally. However it does it, it answers the question of whether or not it wants to replace that content, and it simply responds with, here's the alternate period. So the content insertion mechanisms are pretty straightforward in the way we do it in ATSC3, and it's all because we use essentially adaptive streaming as the base for our IP base for our video and audio. All right, thank you. And I guess Q&A happens a little later.
Thanks very much, Mark. Excuse me, appreciate that. Really enjoyed the inner workings of that whole process and these case scenarios. That was fabulous, thank you. Next up is Dr. Yin Wu. Dr. Wu receives his Master of Engineering and PhD degrees in electrical engineering from Carleton University in Ottawa in 1986 and 1990, respectively. He was a principal research scientist of the Communications Research Centre Canada. Dr. Wu's research interests include broadband multimedia communications, digital broadcasting, and communication systems engineering. He is a fellow of the IEEE and a fellow of the Canadian Academy of Engineering, an adjunct professor of Carleton University and Western University in Canada. Dr. Wu is a member of the Atsc Board of Directors representing IEEE. He is an editor-in-chief of the IEEE Transactions on Broadcasting. He was appointed as a member of the Order of Canada in 2018. So please join me in welcoming Dr. Yin Wu, sorry.
Hello, my name is Yin Wu. I'm a research scientist with the Communications Research Center Canada. It's a government research lab under the Innovation Science and Economic Development Canada. Today, I'm going to talking about ATSC 3.0 transmission layer and 5G convergence. The outline of the presentation is first about the ATSC 3.0 transmission system versus 4G and 5G system. We're going to talking about the Canadian contributions to the ATSC 3.0 development and deployment. There are three technologies we're working on this from Canada. One is the layer division multiplexing. The second one, the in-band distribution link. And the third one, the in-band full duplex inter-tower wireless network. We're going to talking about the convergence of broadcasting and broadband, and we'll draw some conclusions. First, we're talking about the transmission system for ATSC 3.0. Well, what's the innovative technologies implemented in the ATSC physical layer? That's the transmission layer. First, we implemented the so-called low density parity check, LDPC code, up to 64K bit code length. Compared to 5G, the code length is 27 kilobits. So the longer the code length, the better the performance. The second one is a so-called non-uniform cancellation modulation with up to 4K QAM modulation. We'll talk about this later. And the third one is the layered division multiplexing that can efficiently combine robust mobile and high data rate fixed services in one TV channel. By the way, the LDM is a Canadian developed technology. There's also a robust Bootstrap that combines time and frequency domain signaling technologies. The last one is the ATSC3, the system frequency, clock frequency is the same as the 5G. About the non-uniform cancellation, what it looks like. Well, NUC is optimized for a noise channel using multi-carrier OFDM modulation. So the AI-based computer searching technology are used in a couple of days to searching the best constellation. The conventional constellation is like a square. When there's noise, it start to turn. So because noise start to turn, we better design our system constellation result like that one. You can see the distance between these points are different. That's why it's called a non-uniform constellation. That's different with the older technology. They are equally spaced. Performance gain is about 1 dB or 26% of our power saving in comparison to the conventional uniform constellation. By the way, the 5G new radio system has not adopted this technology yet. This curve compares the ATSC physical layer or transmission performance with the 5G. You can see those diamond, blue diamond. You can see the higher the better, the more spectrum efficiency. And you can see they are consistently, the red cross is a little bit better by the blue diamond, not much, about half dB quite consistently. And for the layer division multiplexing, it is a new transmission scheme that overlaps a multiple layer of signals with different power levels for different services and reception conditions. For each LDM layer, there 100% of channel bandwidth and 100% of power and time are used to transmit the multi-layered signals to achieve high spectrum efficiency. So the upper layer is called the core layer. It's for ultra robust HD mobile, portable, and indoor reception. The high data rate enhanced layer, the lower layer, is for 4K UHD and multiple HD fixed reception. So it can cancel the one layer, and the second layer will emerge. They are working on it. So traditionally, as you might know, we had time division multiplexing and the frequency division multiplexing. Looks like this. The program can be multiplexed by time and by frequency, and then by time. And now we throw in a power division. We add another layer, LDM. In the receiver, we're using signal processing technology to separate them and start decoding each layer of the signal. This is a very messy slide. You only need to read the lower two lines, those red fonts. Our hardware test shows the LDM mobile service has about 3.5 times power savings. And for the fixed high data rate services, LDM has about 1.7 times power saving. So power saving means more efficient, more green, and better service quality. Another one is the LDM can do layered transmission. As you might know, there's so-called scalable video coding. So you have a 4K UHD video. You subsample is to lower resolution one, and a difference between the original and the small low resolution video. You have a enhanced layer. So these two layers, we're using the LDM for the mobile and the high data rate layer. So in the transmission, you can directly receive a mobile handheld reception, HD services, and also in the receiving side, you can combine these two layers for 4K UHD. So in one transmission, you can have 4K UHD and HD mobile services together. So this is a transmission layer capacity. So you might know there's a Shannon limit based on information theory. And the low end is for low capacity robust mobile services. High end is for high capacity, less robust, needs rooftop antenna. And the LDM can combine these together to achieve both service quality. So 3.0 in-band distributed link for SFN transmission and bidirectional inter-tower communications. Mobile and handheld services are getting increasingly important for future broadcast services, as well as connected car, IoT, and new applications. For good mobile portable service, multiple transmission tower or single frequency networks are needed. It also needs a studio to transmitter link that to feed all transmitters. This can be achieved by full duplex in-band distribution link, as well as inter-tower communications, a reconfigurable wireless network for SFN broadcasting, in-band inter-tower communications, and IoT datacasting and connected car applications. But it also backward compatible with the ADSC 3.0 systems. That's for the broadcasting service. Here is a traditional example. You have a studio, you feed 4 transmitters, each using a studio to transmission tower link. So traditionally, you're either using dedicated microwave links, but you might not have the spectrum, since most spectrum being given to 5G for deployment, and also install the digital microwaves can be very costly. Another one using fiber links to connect all towers, but it can involve very expensive construction, and also rental costs of the fiber link are also very expensive. And some towers might not be linked by the fiber. So the solution is we're using wireless in-band distribution link to do the job. We come back to the layer division multiplexing. We can show if we have 2 layers. Traditionally, the core layer, the up layer, can provide about 3 720p HD or about 8 high quality standard definition 480p services. That's at the upper layer. The lower layer we can put in maybe 8 720p or 4 1080p full HD. So there are extra capacity we can use for backhaul. That saves telecommunication cost. So for example, we can take piece of the spectrum on the lower layer used as for the program distribution. So also use the supplemental downlink and the emergency services. So this is example how we do it. We're just using part of the in-band spectrum to deliver the program to the tower. So the capacity loss, we doing the in-band distribution, maybe at the beginning we'll need 30%. Then using the more advanced technology, we can reduce it to 15 to 20% of the capacity. So not a big part of it. So how we do it? We can do it step by step, propagating through towers. We have a SFN coverage, so it's scalable. We can also reconfigure it from different ways to each tower, and we can also using different geometry to go this way, different way. So if one tower goes dark for some reason, maybe we can reroute it. So it's a mesh network. So the example shows that by using different distribution routes, information can flow in different directions among broadcast towers. In an SFN broadcast network, it can embed a wireless network among all broadcasting towers. It is actually not just limited to SFN network, it is a tower communication system embedded in a broadcast infrastructure. So each tower can broadcast audio, video, and data services while receiving information from other towers for relay, backhaul, and broadcasting. A broadcast out and single input in system. It is an inter-tower communication network that is independent to any existing telecommunication infrastructure, which can reduce communication costs for broadcasters and survive emergency and nature disaster. So this is how the inter-tower communication can work. So we have 2 broadcasting towers, each with its coverage for single frequency network. And we can, because the tower is really high, we can actually communicate between towers. So the way to do it, several ways. If we're using LDM, we can either using piece of the lower layer to do the job, inter-tower communication and distribution, and we can also do TDM ways to do it. So there are actually 3 different services. Consumer broadcasting services to mobile fixed terminals, and we have SFN distribution link. It's a one-way very high data rate for spectrum efficiency, and we can do an inter-tower communications network. It's a 2-way communications among broadcasting towers, while LDN datacasting in each tower coverage area, and each tower can transmit different data. So this is one example. First, it have an in-band distribution link that's 1-day high data rate to feed the program to each tower. And now we can, to each tower, we can have a 2-way communication to do the data casting and control, co-end control and network monitoring and many other things. So we can have a SFN coverage with data capacity. This is another way is okay. The different towers can broadcasting different data or local programs, local insertion, local advertisement. Or you can also, some of it can broadcast the same content with the main transmitter. And also you can using layer division multiplexing, have 2-layer services. So it's a very flexible configuration. Talking about the 4G and 5G broadcast systems and the convergence of broadcasting and broadband in 5G and beyond. Okay, for 5G, there are lots of 5G talk these days, but as for 5G user cases, they typically listing these 8. And by the way, there's actually a broadcasting services as one of their user case. Here we are talking about broadcasting subsystem within the broadband wireless like 4G, 5G system. Dated back to 2004, there was so-called MBMS system, which means Multimedia Broadcast Multicast Services. It's a point-to-multipoint communication system designed for 3G cellular networks. But that system was not a business success. Later, the technology advanced to the 4G, so there are so-called evolved MBMS system or eMBMS system, also called LTE broadcasting, but the system was not deployed business-wise or commercial-wise. More recently, by 2017, there was so-called FEMBMS, is a further evolved broadcast multicast services. That's for the 4G. And but in the 5G, it also carried this FEMBMS system. Some people call it ENTV in the 5G release 17. In the 5G release 15. But it's not using the 5G new radio transmission system. It's still using the 4G system, but it's got a name for the 4G LTE based 5G broadcasting system. This system is being evaluated in many places, but so far there are no commercial deployment. For there are 2 things we're talking about. People might confuse. One is the broadcasting capability and the broadcasting system. So broadcast capability is in a dense cell environment like 5G. Having point-to-multipoint capability in each cell is a good option to reduce the cell traffic load. This is a signaling easing to allow point-to-multipoint in each cell to deliver high-demand content or services maybe for a charge. The system for 5G is still under development now in the release 16 by 3GPP. Another thing is a broadcast system. For example, today's over-the-air TV system. It is an overlaid network to the broadband wireless system that deliver multimedia entertainment and other services. Where 5G develop and deploy an overlaid high-power, high-tower broadcast TV type of system, well, there's many issues like economy, content, business model, and regulation issues. So there need to be collaboration among industries. 5G and broadcasting. 5G will be an ecosystem that includes many different standards, operating on different spectrum bands, providing different services. 5G is generally designed for small-cell point-to-point communications in densely populated areas. 5G might have a broadcast multicast capability or subsystem, but it is not ready yet. We're talking about the elements of convergence. What is convergence? Different people might have a different thinking and different meaning. Convergence of services and applications is one kind of convergence. Like the whole cell phone system starts with the voice communication. Then they can do data. Then they can have internet access. They can do streaming. They can do video. So that's the evolution path. For the broadcasting, yeah, originally just audio video. Now we can do data. We'll be able to do IoT and other broadcast internet services. Another convergence is a convergence policy, which means traffic management and other protocol-related issues. The last one is convergence of networking. So that we'll talk about later. So this shows the software stack for the Atsc 3.0 and the 5G. You can see there, other than the physical layer, they are very much have many common elements. So for example, both have using the IP transport. They all use HTML5, JavaScript. They have almost the same audio-video codec. So Atsc 3 could be part of 5G ecosystem. Atsc has set up a special group to develop Broadcast Core Network, BCN. It's based on 5G core for the convergence of broadcast and broadband. Broadcast Core Network can be a cloud-based to connect all broadcast facilities. For example, production, distribution, storage, to enable broadcasting and datacasting services, and many more. Atsc also set up an implementation team to work on the inter-tower communication networks and in-band distribution link. So I'll be heading the last group. So here's some concept about how the broadcast core network works. So you can see the lower part, there's 5G core. The upper part, there, Atsc 3.0 cloud. So they all related to the cloud and related to the core network, but it can using the 5G core network infrastructure and standards. So we don't need to invent anything. Actually, the 5G core and 3GPP already defined how the 5G core network to interface with the non-5G compliant other networks. For example, broadcast network is one, and there are also Wi-Fi, there are also satellite, and there are also cable TV system, IPTV system. So there's the interconnectivity issue, not just a broadcasting network. Another one is our plant working on is a so-called smart tower communication network. In the future, a broadcast tower no longer a dumb broadcasting tower. It has a broadcast core network local server. It connects to the gateway to the mighty internet. It can do the storage, data casting, traditional broadcasting, and many new services. So as a conclusion, Atsc3 is the IP-centric broadcast system. It is designed for audio-video data casting to large number of users in widely distributed areas. It can be part of the future wireless ecosystem. 5G is designed for small cell, dense populated network to deal with exponentially increase of data traffic and connectivity. It will need a large cell overlay network to distribute the point to multi-point and broadcast types of services. Atsc 3.0 and 5G can complement each other to contribute to digital economy. That's all my presentation.
So next up is Ann Shelley, Managing Director of Pearl TV, a business organization of 9 broadcast TV companies investing in forward-looking opportunities, including next-gen, and has more than 2 decades of wireless and media industry experience. Ann was a founder and president of APS Context LLC, providing senior-level advisory to some of the nation's largest public media companies. She served previously as a senior advisor to the NAB and as an executive director of the Open Mobile Video Coalition. And also, Ann was also a founding management team member of several companies, including the nation's first commercial digital cellular network, American Personal Communications, DBA Sprint Spectrum, and XDSL Networks. She is a past venture partner and CEO of Acca Wireless. Ann serves currently as a board chair of the ATSC 3.0 Security Alliance, as well as a board member of the Advanced Television Systems Committee, WYPR Maryland's public radio station, and the Wise Giving Alliance, give.org. She formerly served as vice chairman of the Mobile Marketing Association's North American board and founding chair of its video committee, and as a founding member of the advisory board of the Johns Hopkins Winning School of Engineering for Professionals. So thank you, Ann, for joining us, and so take it away. And I think you might be on mute. I think you're on mute there, Ann. There you go. Oh, still can't hear you. I think you're still on mute there, Ann.
Okay. I was muted by the, just to say, I was muted by the organizer, so I was in a battle.
Apologies.
So,
you're good to go.
It's close to 8:30 here on the East Coast. So it's a pleasure to be here to talk about next generation television. I'm going to focus on the commercial deployment and what's happening in the U.S. You heard some good stuff from Malin Nolan and Mark Corral on sort of, you know, the attributes of sort of how we got to next gen. And I'm going to talk about what broadcasters have been doing to commercialize it here in the U.S., where we stand on that commercialization, what it means to broadcasters here, and I think how that translates to opportunities for Canada, and certainly the great work that's happening at Humboldt with looking at next gen as it would apply to a Canadian marketplace. So let's see. There we go. So just to talk a little bit about Pearl, we're a business organization that was formed over 10 years ago. We represent 9 of the major station groups in the United States. These are the companies that they're affiliates of the networks. We have over 750 stations nationwide, and we cover over 75% of US households. These guys book over $4 billion in ad revenues annually. It's a large group of companies. We've been working together over the last 10 years as our senior executives recognized that their viewers, largely for their live linear broadcast news and local information, as well as the events and sports program that they bring every day to communities in the US. The consumers were shifting viewership, that ad dollars were an ad-supported business plus a distribution to cable in the US. With the advent of streaming, iPhones, and other devices and methodologies for receiving content, that we need to keep pace with that. So we've been involved in a lot of work looking at smart TVs over the last 10 years. We tried to do mobile, the MH technology and 1.0, actually launched in 14 markets and took that out to consumers. And we turned our attention to Atsc over 6 years ago, recognizing we needed a better mousetrap than we currently have today. As we started developing and working closely with all the companies at the Atsc, what we brought to the process was a business model perspective for broadcasters and the standardization of our new transmission system. We also looked heavily at the consumer. We probably conducted over 10 surveys, or 5, maybe 8 surveys in the process, and we held extensive consumer labs testing the features and functions in next gen and what would drive a consumer to be interested in next generation television. We're in a very different environment in the US. This is not mandated like the last transition was, as it was explained earlier. It's voluntary for the consumer, voluntary for the TV manufacturer, and voluntary for broadcasters to transition to next gen. So over 3 years ago, recognizing that we needed to develop the methodologies and do the proof points and proofs of concept around the product and services, we formed a model market in Phoenix. That model market's partnership included all of the networks, as well as many, many partners. We have some of them listed here, Trivinny being one of our key partners in that effort. The other 3 that I'm going to mention are critical to our success are Samsung, LG, and Sony. In this process, what we worked on was first, how do you transition collectively and collaboratively where we are sharing spectrum amongst one another? Atsc is not backward compatible. We solved that by launching a station in Phoenix to do that very thing. And proved out amongst broadcasters we could do those agreements amongst one another to enable next gen. We also started working on the actual product and services, and since have published service profiles, and there's a great, and I should have had the website here, our website, but there's a broadcast manual. It's in its, I think, 8th edition. Everything you would ever want to know from an engineer's perspective on how to enable a US-based next generation television broadcast station based on the service profiles that we published out of Phoenix. So how are we viewing next generation? So I mentioned that we have been working on the development side. 2020 was our big year for operationalizing next generation. We went out with 20 markets despite COVID. We had goals for 40 last year, and I'm pretty proud of the fact that we were able to enable 20, I'd like to say 20 in 2020. We didn't plan that. There were also 20 models from the TV manufacturers in 2020. So I don't know how we got that all right, but we did. So the receivers that were announced at CES in 2020 were really important because they started to drive these launches. Now, what's interesting is these receivers went out without any marketing. I can't reveal the number, but we blew the doors off of the projections from CTA, and I'll get to those in a second. Largely because consumers were pent up. I mean, the demand outstripped the supply for televisions this year due to COVID, and we kind of caught that wave. And that's going to happen again in 2021. But part of what we're doing is we're launching these stations, we're stabilizing the service. And that service is a basic 1080p as a start because of spectrum constraints and the lack of 4K content. The audio Dolby transmission system, which is inherent in every single television, and a basic common application that's being deployed by broadcasters on a test basis right now, and will be more fully deployed towards the end of this year, that enables some of the interactive applications that were discussed earlier by Mark. This is sort of what I call the starter kit of TV services that we are testing in marketplace right now with consumers. And I'll talk a little bit more about some recent results coming out of a 5-market on-air consumer campaign. So that's where we currently are. And so as you look going into 2021, more TVs were announced at CES. We're launching more markets, and by this holiday season, it's really where you'll see the hockey stick take off for next gen. So just a quick look at the markets that are scheduled to go on. There is a website I'll get to that you can follow in the US to see the progress. So you can even drill down in each city and see how many channels are on air as we continue to add stations. So 2020 markets listed to the left. This is the first half of 2021. Those are markets going on that we are scheduled as of right now, and then the second half of 2021. So that gives you that significant coverage. There's more markets than this listed that actually pull us over the 65% household coverage. We just didn't list those. You know, it continues to roll out, and you know, we're pleased to see the progress. This is a real story from my perspective, the receiver availability. This was announced by CES at the CES show. Their projections for in-home next-gen enabled television sets. We actually, if you look at the 2021, we're going to be well over that in 2021. So I see that number moving forward and actually conceivably being closer to 35 to 40 million by 2024. And this is because the economics of the inclusion of a next-gen TV receivers is far different than what you saw in the DTV to the analog to DTV transition. The lowest price set this year, and we came out on higher end models, was at $850, and you're going to see lower price sets coming out this year, and then more competition from the 3 manufacturers from other vendors or OEMs in 2022, and we know of those OEMs, so I can make that statement, but I can't announce it. So all good news for us. With this, the importance of this is the addressability, right? So Mark mentioned the application environment, that hybrid TV environment. That's where broadcasters can monetize and get the return on the build outs pretty quickly into 2023 as you start to get something over 15 million sets with returnable data from the application and viewership information and the ability to launch more. One thing that Mark, you also saw Mark's information was the content security protection. That's something broadcasters have never had before. That really allows the ability to not only protect our signal from hacking, but also protect the content that's being distributed over this new platform from being pirated. But it gives us other additional tools around being able to launch unique sort of secondary pay offerings and things like that. So as OTA rises in the US, which is happening, we can really monetize that unconnected OTA user. I mean, when I say unconnected, today we have no connection to the consumer. So it's that direct relationship that we'll be getting with this application environment. I mentioned that we had, so again, personalization recommendations. a more modernized guide, deep linking, integration to portals and apps. There's just a whole host of things we can do. We are, as I mentioned, have developed a what we call the framework that would work across the plumbing, if you will. Pearl and the Phoenix partners have been building the industry plumbing that then will allow for open sourced application development for application developers to come in. We did announce at CES that we were working with 7 right now, including IBM's Weather that's working on the framework. And this is essentially accessing the libraries, as you saw in Mark's earlier diagrams, that then can be used to create widgets that would be served by broadcasters in their markets for different applications. Think sports betting is what we're working on, and shopping and other capabilities. So how does the consumer know about this? This is something really unique and for broadcasters as well. The CTA, and work with NAB and with Pearl and the Phoenix partners, developed the next generation TV logo. This is a logo conformance program where manufacturers, if they want to carry this logo, must meet a self-certification process that matches up against our service profile. So a tremendous amount of collaboration happening in the industry. It includes the Atsc, who is helping to develop the I would guess the hierarchy of the testing that gets done as we work with manufacturers. This is incredibly important because this is not a one and done standard. We will continue to roll out features to consumers over time. That's why, with the beauty of this, is we didn't have to have it all done day one. We had to have enough to entice the consumer to want to buy a television, which is exactly what's happening in the marketplace right now, because they can go down to Best Buy and buy one. But we can continue to make it better. And so if you go to watchnextgentv.com, you'll see the ad campaign that was launched in 5 markets over the holiday season. The response to the ad campaign was over 70% of consumers said they would go buy a next generation TV based on this advertisement. In it, we talk about the features that resonated most through our consumer work, which was upgradability. The fact that this continues to get improved is a huge selling factor. Obviously, they expect the better video quality. Every TV they buy is better and better, and content is getting better and better as it's produced in. But that was somewhat secondary to audio. The Dolby audio system, again, outperformed in expectations in terms of what consumers are looking for. That's what's called Voice Plus on this system. It includes the ability to boost the voice over the background noise, as well as consistent loudness. What we like about these features is there's no production required. It's part of the TV set and the broadcast in NextGen. And then lastly, what I was surprised at, and we have not released this consumer data, it was just run last week, but I'm letting you know now, interactive. The interactive application, if you watch the ad, we showed 2 examples of interactive. One is a cooking show that was actually demonstrated with CBS called The Dish. And then the second was sports stats. And consumers came back and ranked that right up there as a leading factor. And that was largely millennials and Gen Zs coming in on that. And what's interesting is interactive has risen overall in the US marketplace because of COVID. Consumers are home and they are engaging more with their television than they ever have before. So all of this is good news for NextGen. You'll be seeing more of this marketing effort as we roll it out in earnest in 2021 in partnership with the manufacturers. And that's currently what's happening in the US. And that's all I have to report on sort of the latest and greatest from the commercialization of the platform.
That's great. Thanks very much, Anne. Really appreciate that, your insight into the business case, a very important component of this whole enterprise in order to make it successful for all. Just wanted to give you an update. We will not be going back to Dr. Wu. He's having some connectivity issues, obviously. What we will do, however, is he has supplied us with a PowerPoint that's got embedded video, and we'll be including that in the recording of this session, and it'll be available on YouTube, on the SMPTE Toronto YouTube in a few days. I think we'll send out a link when that's ready to go. But at this time, we will take questions. So I'm just going to hand it over to you, Peter, if you want to go for it. Thanks.
Thank you. The first question we have is from Martin, and he says, promising business benefits, but where is the CRTC on making industry and stakeholders decisions? Is there anyone who wants to take that from our presenters? You can all turn your cameras on.
I could speak to that. Hi, Peter, it's Orest. I could speak to it from an evolutionary standpoint as I've come on board to with the effort with the Humber Lab. At our Humber seminar, we did invite ICED and CRTC, and they both attended, and it was a very very positive response. I think that there are steps being taken towards understanding how it can play into the Canadian system in terms of regulatory policy. So I do think that there are eyes on it at this point. I'm not sure where that process is, but I do believe it's being considered in a way that will hopefully allow for further conversation with stakeholders.
Okay, all right.
And ICED has also polled some broadcasters as to their interest in government support.
Okay. Another question from Martin. He says, does SFN be of benefit for the edge contour with 5G in high density cities, but will it be of benefit with current cable saturation? Does that make anyone want to go?
This is Anne. Just to mention, some things I didn't mention were sort of beyond the commercialization of the service in the next 2 years, other things that we're working on in the US. So we do have an SFN system for next generation TV built in Phoenix. We are testing out that system. One thing we did do is do an auto implementation test with Sony that has an auto module, and it performed really, really well. We did it with SFN off. We're now going to go back and do it with the SFN on. What we see the SFN's benefit for broadcast in the next gen environment is it's a capacity builder for us. It adds more capacity to our platform, and with that capacity, the over-the-air, the ability to do more over-the-air with whether it's multiple channels or more channels we're providing, or it's non-real-time data delivery that Mark talked about that's being worked on in Detroit for delivery of files to auto. It creates a robustness factor in the market for us with not a lot of additional capital to deploy when you're looking at the next gen TV deployment of sort of in that market. We would only need 3 SFN to really cover the market well. And the US has a proceeding that it just approved to allow us to have more flexibility, outside our contours into the interference area for next gen, recognizing its value. So that's the US sort of situation.
Okay. Anyone want to, Orest, you want to speak to Canada?
I think Yeon is actually hoping to speak, but I believe he may be muted at your end.
Oh, try now.
Yeah, I'm okay now. Yeah, so I think SFN definitely works better than without using SFN because, cell phone industry know that 40 years ago, they are running a multi-tower network. Broadcasters in Canada up to now still using one stick. So there's no brainer. If you have more tower, you have better service quality. There's no doubt about it. That also relate to the regulation issue, as like up to now, Canada haven't working on this SFN issue yet, but the US just changed their rule. So about SFN, I think Canada probably will follow very soon.
Okay, good. So this one probably for you, Dr. Wu, as well. Does the enhanced layer of LDM has to be announced in Bootstrap in order to be discovered by the receiver?
Yes, Bootstrap is all the signaling is in the Bootstrap, because compared to 4G and 5G, they have a signaling channel. In Atsc3, like the Bootstrap is equivalent to a signaling channel. Signaling channel, the Bootstrap will tell you how many layers have, how many PRP have. PRP means physical layer pipeline. It's just signal. So all the signal structure is described in the Bootstrap. So that's one of the goodies for the new Atsc3 system compared to the old one.
Okay. There's a comment from Martin. He says, another benefit of SDN to now manage software-defined TV. APIs, anyone?
Certainly, with the more processing power, the new graphic and AI chips, like probably we're a few years away, we have a totally software-defined TV. Because the power work, but now we're using the chip because there's tremendous computation power sitting in this small box. Like a 2 by 2 millimeter silicon can do so many things. But when you turn into a software, right now the AI chips, graphic chip are very powerful, but still a little bit step away from the software-defined multimedia, broadband multimedia system, but we were getting there. Another issue is the cost. Graphic chip is much more costly than a silicon chip costs you less than $2.
Right. I actually don't have any other questions. Is there anyone else out there who wants to ask a question? Nobody's asking any questions. Riza, do you have a question or a thought?
Hey, Peter, Tony here. I've got one.
Sure.
Just a question, because we're in Toronto, we're so close to the Buffalo-Rochester border, and I guess Detroit, Windsor in the same vein. Is there anything cross-border that will limit the over-the-air transmission from those transmitters into our sector? Is this going to be a user login account scenario where TVs are going to have a login or credentials to be able to tap into the?
Yeah, you just would have to have a next gen and enabled TV that has the US based implementation in order to receive it, because there is content security protection, and those US TVs have that. Without the receiver chip in it, you couldn't get it. So, but it has to be turned on. So there won't be sold with next gen, I don't think, in Canada. But I guess a lot of people drive over the border and pick one up and bring it over, and then you certainly could get it. It's free over the air, so there's no login. So think like web certificates.
There might be a parental control.
Well, there's all the U.S. rules apply. It's no different than basic free over-the-air service. It just has the protections for the content on it, so that it can't be pirated like it used to be in Canada. So you can't steal it, but the consumer can view it on that device without knowing that there's anything there. Does that make sense?
Well, yeah, well, right now, anything that comes across the border, signal-wise, it's a free over-the-air, and
It's free over the air. But you would need an ATSC 3.0 enabled or next gen enabled television. Right. Yeah.
You have to drive to the Best Buy in Buffalo and pick one up.
You have to get a US based one. Yeah, the ones that are available in Canada, they don't say anything about it. They may have the tech in it, but it's not turned on.
But you can go to the bestbuy.com, not bestbuy.ca. You know, that's a difference.
Or you get it off of Amazon.
All should buy off of our website. www.watchnextgentv.com.
So is the end game for the broadcasters to have multiple channels that they don't currently have to deliver content to the home, augmenting the cable system potentially?
It's a hybrid TV environment that allows us to monetize the content in ways similar to what we could do on a streaming platform, but utilizing the power of broadcast. So we can do more. It's basically we're able to lever our over-the-air services. Right now, we're in a paid environment with cable, but here today on One Data, we don't know who's watching. We can't personalize or provide, personalized information. The consumer opted in. We don't have data on that viewership, and so here we're able to do more. We're able to do addressable advertising, which is really moving quickly in the US for live linear. And there's a whole host of things we can do. We enable application environments, shopping, all kinds of things that can happen on the over-the-air channel that could not before. And these applications, these formats for next generation television are also enabled on cable. So there's things that are in our platform that are actually nice upgrades for the cable viewer, such as the audio, the ability to choose various audio feeds, things like that. So we have done an integration with Comcast in Phoenix, and we're working closely with Comcast Charter and Cox on that integration, bringing the best of the formats in next gen to cable, as well as to other virtual MVPD distribution platforms.
Yeah, in specific though, there's even more specific in terms of what is in the signal. It's HEVC now, so we can get better compression. We can get more services packed into it. Plus the way the broadcast now, there's a whole bunch of different operating points, but we can get more bandwidth out of the broadcast signal, including the LDM.
Yeah, so that allows us to do 4K. It allows us to do, higher quality, but also more channels.
Yeah, so skinny bundles are possible, right?
Yeah, we can launch virtual channels inside of our channels. Right. I mean, it's endless possibilities. So, there's a whole, Diginets or multicast is really taken off in the US. There's more multicast launching than ever. It really allows us to monetize the over-the-air platform, which we were doing only on an ad basis, and on the old sort of GRP basis, and addressable is the future, and so that ability to actually address a device is unique for this platform.
I think, sorry, just to add to Anne's comment and everyone's comment, I think there's an interesting contrast that may develop in Canada, and it's hard to say, but then the go-to market strategy in Canada may initially not be front-facing television in the sense of television applications. There might be some pivot points where we move into data casting and move into working with the network in a broadcast unicast model. So we've created pivot points in the lab structure to allow industry partners to choose the piece that works best for their own ROI. It could be that television is, maybe not first in line, it might be second in line or third in line. So we realize that the broadcast industry is different in Canada than it is in the US for a number of reasons.
Yeah, and I'm looking forward to those innovations you're going to do, because what we're building in the US, so the content security platform would apply for Canada. It could be utilized. It's actually open for Canada and Mexico, and you would need that if you're like Coursera courses that need to be protected. So that's available. So a lot of what we're doing is building the plumbing that would allow for, so a lot of what Mark Kroll talked about is, a live linear broadcast, it could be a live linear broadcast, it could be coursework, it could be telehealth, it could be whatever. It's a file, it's data, but the underlying plumbing and distribution technologies, what Madeline talked about, the core network in the US, there will be cloud integration. We're looking at that for auto in Detroit. So, it gives flexibility here too. Broadcasters can pivot and have a platform that allows them to be able to address the file or data distribution aspects of the marketplace at that moment in time. So we're not stagnant. That's what's fabulous about this platform. So I'm excited that you guys are going to do what you're going to do. It'll probably help us in our data distribution side of the house.
And plus we get the India aspect too, where they're looking at more mobile, right? So we've got even that is a different pivot than what you're talking about.
Yeah, but if you watch the wireless industry, the mobile payments model did not come out of the US, it came out of Africa.
Right.
So that's where mobile payments were driven from originally. So, we've got potentially that same thing going. That's why I was so excited about what you're doing, Oris, with Humboldt.
So Steve asks, what are the barriers to having Canadian conventional television broadcasters start testing or adopting ATSC 3.0? So I think financial is probably one of them, but what else?
I think in some respects, it's probably a question for the broadcasters if they see the ROI in it. From a policy standpoint, I can't speak to that well enough at this point, but I do believe that one of the things that we're aiming for at the lab is to show innovation and facilitation and deployment at the lab and in the space as an intersection for Canadian industry to help attract greater sort of levels of education and advocacy for the standard, and that can help be a catalyst for it. So I can't speak to exactly where the policy discussions are, but I know that if we can show innovation in the space and show new introductions, that can help trigger the conversation.
Right.
Just a point on the capital piece of it. In the US, the majority of the stations that are transitioning in this first round were the transmitter was upgraded due to the repack by virtue of access to funds. The average cost for a station upgrade is around $250,000 to $300,000, which is really not a lot. But that's assuming that transmitter had been upgraded via the repack. But what I'm also seeing happening right now in the United States, a lot of transmitters are at the end of their life anyway, and a lot of equipment, and so they're being replaced with newer transmitters, newer encoders that are software enabled for next gen. So that's also an interesting consideration for Canada as you're looking at CapEx.
Right, and a lot of the systems, as I mentioned when I was talking about the studio equipment, all of it's being virtualized, all of it, and you can run. In fact, we're doing India demos right now. And they're running entirely. There's 2 of them running right now, and they're all running out of the cloud. They're being sourced from San Francisco, running in Singapore, and ending up in Delhi. So, all of the systems and all of the software are just running in virtual environments, and you can either have that on premise or you can run it in the cloud and pick and choose however you want to do it. So I think that helps a lot in terms of experimentation. Because you could just run up buy a server and run a bunch of VMs on it, and all of a sudden you've got an experiment running. Or you can buy the equipment and rack it and stack it and do all of that kind of stuff, up to you. It's really very, very, very flexible at this point.
Yeah, one of the things that's really one of the most fun things for me is watching what different vendors and what different technical providers, what different countries, different use cases are coming up with for this standard. So I'm going to be tremendously excited to see what happens at Humber. Wait till the students get their hands on this thing. They're going to be thinking of things that us old folks have never thought of. And we'll see what happens in India and other countries, and what's happening in the US as well. It's all really innovative, and the platform just allows you to do a variety of things. So, I think the market is going to drive it in terms of what types of things this standard is going to do for a given region or country. And it's going to be really fascinating to see what happens in Toronto, in both at what's happening in CRC, in Ottawa, as well as what's happening in Humber. Jan didn't get to talk entirely about the ITC IDL stuff. I know it's just a bunch of alphabet soup, but I strongly encourage people to watch the embedded video with the PowerPoint that's going to be provided, because that's another fascinating innovation coming out of Canada that I'm pretty sure is going to be exported once it gets kind of solidified. So it's pretty interesting to see what's happening out there with this thing.
I think one thing, just to add to Madeline's comment, is I took some sage perspective from learning about ATSC3 early on, and at the end of the day, the bottom line, there's really prime spectrum that's out there that's being underutilized, and there are ways to make much more efficient use of it. And I think sooner or later, it's something that that does sort of move forward in terms of a call to action to do something with that space.
Okay. Guy asked a question here. In ATSC 3.0, is there any hooks to support any conditional access system?
Yes. That's what Mark
Short answer.
So that's it's content security protection that is enabled by the standard, and it was developed by broadcasters, and you can go to an organization called the A3SA and find out all about how that's implemented in the US for next gen. But the answer is yes.
Okay.
Yeah, and I think one of the things about ATSC3 is that we really worked hard on the convergence piece. And so the content security is based on common encryption, which is the encryption system used for streaming services, which is baked into many, many devices, all devices perhaps. So yes, there is absolutely conditional access, as Anne points out, and it's based on CENC, which hopefully makes it easier for implementation.
Yeah, it's wide.
Okay, good. Willie says, can we put 4 times 1920 by 1080 or only 2? I think that was a question directly to something that someone said.
I think the simple answer, you can easily put the 1080p 4 times in ATSC3 in 1.6 max. And if you do the statistical, statistical multiplexing, you go 5.
We have 5 running with StatMux.
Yeah, statistical multiplexing at 20%. That's another channel.
So we have 5 running in most markets with that are we're stacking them. We have 5 running with StatMux.
Okay.
And I think it's interesting to point out that in South Korea, they've already successfully transmitted 8K over ATSC3 in a 6 megahertz band with HEVC using MIMO and channel bonding. So it's going to be very interesting to see what happens.
That's pretty impressive, yeah. Willie says, wow, 5. He's happy to hear that. I have one more. Tasha says, how would this affect rural views who don't have access to 5G or faster internet? This was
so
around 9 o'clock.
You want to answer that, Madeline? There's a company called Evoca who is actually doing small market deployments, and they have a different business model, which is similar to being a MVPD, using low power stations to enable next generation television services with a box that they built that they're distributed to consumers. It's less expensive and a better service that's being provided by satellite right now in those markets. The other thing is we have another player, Gray, that's testing in a small market, Tallahassee, which is pretty small. Various services and capabilities, non-real time, looking at different business models and opportunities for the rural market. One of the problems that we have in rural is there's not a lot of television spectrum allocated, and so the tricky part will be being able to figure out how to do a transition. One of the things that's really important to understand is that the regulations in the U.S. require us to simulcast our 1.0 into 3.0. The U.S. regulators are concerned about the consumer's continued viewership of a quality 1.0 service as we're transitioning, and also that 3.0 is readily available to consumers. So it's sort of this, it's an interesting problem, or we'll probably be working with the Commission over the next 3 to 4 years to figure out what the end transition game is. This Commission did not decide to call it. They wanted to see how the market progressed, which I think was wise. And they'll be coming out with a proceeding in the by next summer that will ask questions around an end game for a transition and simulcast and these other considerations which would affect availability spectrum in rural markets.
And one other thing that I'd like to add to that is that some of the work that is going to be happening in Humber with this concept of convergence is being worked on. So for example, in Indiana, they're working on this concept of distance learning. And their original plan was that they would help with the COVID issue with distance learning over the broadcast for students that have no broadband at all. But what in fact they're finding is that the more prevalent use case is that the students have minimal broadband. So for example, the only internet connection in the house might be mom's cell phone. And mom's cell phone cannot serve 3 kids their classes all at once and all kinds of interactivity and still be on the phone and send texts or anything like that. So what they're looking at is this sort of converged system whereby the broadcast is used for the sort of classroom lectures and the videos and all this, and the test itself is all coming over broadcast. And then when the student completes the test and they want to send it back, they use the broadband, which in this case is the limited, 1 cell phone or perhaps a DSL line or something like that. So the other thing that I think is worth thinking about in the rural use case is that if we're not expecting to have 5G rolled out in rural areas tomorrow, we may have some limited two-way network available, perhaps a satellite system or a DSL system or a single cell phone in the house. You can supplement that with the broadcast, where the large amount of data that's coming from the downlink can be carried by the broadcast. What that really does is it optimizes that narrow two-way network for two-way traffic. So it sort of takes the load off, if you will. And I think that's an interesting use case for rural as well.
Yeah, we're actually, on that same topic, we're actually building something right now that's based on the Zinwell box, in fact, Madeline, that you talked about or had on your list of devices. It actually has an ability, there's one of their versions as an LTE connection. It actually has a cell connection built into it. So the back channel can actually be the cellular system out of that set-top box. So it has a broadcast downlink for ATSC3 and an LTE connection back. And so we're actually experimenting with that in an educational setting, exactly as you described. We're building that now to experiment with. So that's actually kind of fascinating, and it really, that box, it won't have 5G, but it'll have, a 3G, 4G LTE capability, and a very likely a slow speed. And so the interesting part is, can governments or, schools or something like that just offer up the data service, right? Just do a big bulk buy of the data service and enable these boxes and put them into rural homes or into disenfranchised homes and have them, without even having the cell phone in the house, actually enable that kind of technology, right? So it's really interesting how that can play.
Okay, one last question. This will be the last question. Do end devices need a full-time internet connection to operate?
No, absolutely not.
No. It's even the security is available to an unconnected device. That was the big problem we solved with Widevine. That's the development we did. That's kind of groundbreaking. So it could be to a connected or unconnected device. You can't receive the data, you can't deliver other things, but you could send files that are secure to an unconnected device.
Okay. Tony, I turn it over to you.
Yeah, wow, pretty good. Definitely got the questions going. I'm still going to look on the internet for a black box that I'm assuming they're going to have some set-top boxes that I can plug into my existing TV to do some of that stuff, I'm hoping.
Yeah, there's a couple that I featured in my presentation. There's a Zapper box and HD Connect Home Run 4K, which are available now.
Perfect.
Yeah,
Perfect.
there'll be more accessories coming down the pike that'll be less expensive, more consumer affordable also.
Yeah, they're all pretty pricey right now, but
yeah, those are really early kind of, but they're perfect for engineers that fool around.
yeah, exactly.
Not for your average.
You could always
a
come
Raspberry Pi computer and off we go.
You could always come to Humber, Tony.
Oh, there you go. There you go. Alrighty. Okay. Well, if I can thank everybody here for being part of our March meeting, I really appreciate it. And again, we will have this recorded session on our YouTube channel in a few days. Just a couple of things, just in closing, again, just want to add to our TTC that we're going to have in June. Maybe there's an opportunity here, Ors, to give an update as to what's happening in Canada. Same with Dr. Wu as to what's happening on the ATSC3 for our conference. Again, a couple of links here for a call for papers and call for sponsors. We'll have an official email blast going out with all this information in, so you don't have to write some of these links down. They'll be coming at you within the next couple of days. Just to give you, again, the recording will be put together. Peter will work on that in the next couple of days.
Yes, and I will put in Dr. Wu's full presentation. So everything you said, Dr. Wu, will be there from the presentation for tonight.
Perfect. Just on a SMPTE note, the election process is going to be starting up in a couple of weeks or possibly next week. So do watch the notice from Home Office come through. Next meetings, April 13th, we have one on the topic of low Earth orbit satellites, LEO. We've got presenters to speak to the new Starlight and Telsat offerings. May will be latest display technologies and signage. And again, June will be our technical conference. Just some information here. If you want to get to our website, that's where it is. If you need some, again, we're always looking for new members, but if there's been some situations here where you've been laid off or retired or furloughed, please reach out and we can assist in some of that costs. Become a friend, there's a URL, our social channels, emails, SMPTEToronto@outlook.com. And yes, again, we're still hoping for the lockdowns to disappear all around. But until then, be well, stay safe, and that's a wrap. Thanks again very much to everybody for attending and all the presenters and our co-organizers. Thank you.